Well, I put up a lot of things on the board. We carry on with the discussion. In the interlude, I put up a lot of things on the board. I have written, okay, the main topic continues to be definite integrals. The geometrical interpretation of the definite integral, which we defined to be the limiting value of an infinite sum, if that limit exists. And here will be written that a to b fx dx, which we have done a little while ago, is the area under the curve of y is equal to fx between x is equal to a to x is equal to b and the horizontal x-axis. Now, this can be shown to be equal to capital FB minus capital FA, where capital Fx is an antiderivative of small fx. In other words, if we differentiate capital Fx, ddx of capital Fx is small fx. This is a very, very important theorem. It's called the fundamental theorem of the integral calculus. It is due to Carl Friedrich Gauss, whose name appears in many, many branches of mathematics, especially in complex numbers. We have two other fundamental theorems of mathematics, one of arithmetic and one of algebra. Both are due to Carl Friedrich Gauss. Even this fundamental theorem of the integral calculus is due to Carl Friedrich Gauss, and he is a very, very important person. I cannot overemphasize on that fact. But the important thing is to appreciate that this relation is not the definition of a definite integral a to b fx dx. That is very, very important, because I have seen in my classes, whenever I walk into a class and ask students, how can we define the definite integral a to b fx dx, the answers are inevitably two. One is a to b fx dx is something like this, sir. And the other is, it represents the area under a curve y is equal to fx between the ordinates that x is equal to a, x is equal to b and the x-axis. That is the geometrical interpretation of this definite integral. It's not a definition. The definition is what we have done a little while ago, and I am prepared to write it down again, that this is defined to be the limiting value as h tends to 0, h times sigma f a plus rh, r starting at 0, r going all the way up to n minus 1, under the condition that nh is equal to b minus a. This is very, very important, as we've emphasized earlier. This is the definition of a to b fx dx. Nothing else serves as a definition, and we of course add that provided the limit exists, because in certain situations, we will see when we talk about improper integrals or infinite integrals, that this limiting value may not exist for certain values of fx, for certain limits. So those are special topics which we will cover gradually. But we say that if the limit exists, then this infinite sum described, because we have seen that as h tends to 0, n tends to infinity, that we have done a little while ago. So here we have the geometrical interpretation, the fundamental theorem and the definition, all packaged into a single basket. Now we will gradually move into demonstrating how the definition can be used to advantage to evaluate certain definite integrals, of which advantageously we know the result beforehand. So we will see how this definition does indeed give us the expected results, and I repeat that we will use this definition to do a few problems of which the results are known. So there will be, quite a bit of faith generated on this definition. We now begin with a basket of 3 or 4 problems where we will utilize the definition to evaluate certain definite integrals of which the results are fortunately known. So it will be more of a verification as well that the definition does indeed work. Now, for example, the first problem I put up on the board is show from definition or show from first principles that the integral a to b x dx is b square minus a square by 2. Now, we all of us know that if we integrate x, the result is x square by 2, and if we substitute the upper and lower limits, the result is indeed b square by 2 minus a square by 2. So, that is what we are trying to show. Now, we have to establish this by using the definition of a definite integral. This application of the formula has to be followed very carefully. That's why I picked up a basket of 3 or 4 problems, which we will do one by one and see that the flavor of the problem, the way it is tackled, remains the same. But of course, different reasonings will come into force, come into play, really. We say that from definition a to b x dx, and this is our fx. Fx is nothing but x, is limiting value as h tends to 0 of h sigma f of a plus rh. If fx is x, then f of a plus rh is nothing but a plus rh. So we will write a plus rh. R starting from 0 and R going all the way up to n minus 1. So we have put this definition on the board, and we must not forget that nh is equal to b minus a. This is a very, very important provision that is necessary. So we are back with the definition. Fx is x, and this is f of a plus rh. It's simply a plus rh. Now, our task is over if we can evaluate this limit and prove that the limit exists. If it does exist, we must find a value. We will explode that sigma form sum. This is a compacted sum. It makes sense here to explode that into its various parts, and then the sum can be tackled. So that is equal to, if we put an asterisk here and write from the asterisk that sum is equal to the limiting value as h tends to 0, h times. First term is a plus 0h, so a, plus second term is a plus 1h. Third term is a plus 2h. Next term will be a plus 3h, and ultimately we go to the last term is a plus n minus 1 h. This is the last term. Now we write this as equal to, being equal to the limiting value as h tends to 0, h times every term has an a. Every term in brackets, including this one, which is not in brackets, we can put it in brackets. So there is one a. There are evidently n terms. So, if we collect all the n's together, there are n a's that add up to na. Fine. Then we see, if we put an h as common, there is a 1h, there is a 2h, there is a 3h, and there are actually up to, so 1 plus 2 plus 3 all the way up to n minus 1. So many h's. And this we can put in larger brackets. This is the starting, this is the ending. Now we write this as being equal to limiting value as h tends to 0, na plus h times the sum of the first n minus 1 natural numbers. Had this been n, we would have written n into n plus 1 by 2, but this is n minus 1. So the sum of the first n minus 1 natural numbers is n minus 1 into n by 2. We close this. This we write as limiting value as h tends to 0. Now we transport the h inside. This we write is a into nh plus, this will be h square by 2, h square by 2. This n and n minus 1. Close this bracket. Now, if we have done all the work from here to this correctly, we can afford to rub out a bit of the work that we've done up, so that we can carry this work right up and carry it through till we reach home. It should be stated very frankly that after we apply this definition formula, the rest of it is purely algebra, but there is a bit of manipulation that is important and necessary. Otherwise, one keeps on looking at these expressions and finds it difficult to reach home. Now, we will take this up here and write this as being equal to bracket A. We recall that NH is B minus A. So we just replace NH by B minus A. Plus, here we have H squared term. This 2 is part of this expression. So H squared, and there is a half, so we write the half here. And the H square, we put one H along with this N, the other H with N minus 1. So we write NH and NH minus H. And close the bracket. So this is equal to bracket AB minus A square plus half. NH is B minus A. And we have a limiting value as H tends to 0. So once we apply that, we will collapse this term only to NH, which is B minus A, and ignore this. Ignore this. Since H tends to 0. So this is what we have. We put the bracket here. So really what we have is, we have to take an LCM of 2. 2AB minus 2A square plus b minus a whole square, that is b square plus a square minus 2ab. And this neatly breaks down to, let's see, this 2ab annihilates this 2ab. There is a b square that survives and a minus a square, because this is minus 2a square and this is plus a square. So what we have is ultimately b square minus a square by 2. And here we have the strength to write the following. We just write as expected. So here we are feeling the formula. It's more like feeling the formula and getting convinced ourselves that yes, indeed, application of definite integrals, evaluation of definite integrals by using the definition given is nothing other than what we have learned earlier.